Okay, so welcome back everybody after the lunch break. We will continue with some really interesting stuff, I think. Let's welcome Benedikt Stockebrand. He's an old IPv6 guy, which in terms of ER&W is quite impressive because we also love IPv6. Yeah, and he's also an old school IT security professional and is now dealing with hardware. And he will present about a new piece of hardware he's creating that's implementing some kind of secure random number generator. So, Benedikt, it's your time.
Thank you. Okay, is this on? Yeah. Okay, good. Yeah, so what I want to talk about, not about my latest contraption as much, but what I've learned while building it, because this is really, the reason why I built it was just for the fun and to learn things, rather than to build a product I could sell afterwards and have to go to conferences, do some sort of marketing speak or whatever. Yeah, so what I want to talk about is hardware you can trust. And I guess, hang on, where's she? Hey, there. Hardware you can audit and then trust. Because you can't audit it, you shouldn't trust it. What really drove me to play around with this was the question, how far can I go if I still want to make sure that what I built is auditable? It's tricky, and sometimes you run into weird problems, and yeah, let's start like this. So, marketing. Sorry about that. I've got a degree in computer science from University of Dortmund some long time ago. Did mostly theoretical computer science there, which turns out to be helpful for a couple of things sometimes. But otherwise, my focus is on operations, TCP/IP, networks, Unix. Security is not there for a reason. I use the same slide for other things as well, and I have this habit of refusing to consider security dedicated topic on its own right in most situations, because I think having a security department in a company is often, not always, but often counterproductive, because everybody else decides, okay, this is not my department anymore, and then things really go wrong. So that's why it doesn't say anything about security there. In 2003, I specialized some more on IPv6, and about a year and a half ago, some people stopped laughing at me, finally. A couple of years ago, I've written a security study for the Federal Office for IT Security, which has been mentioned here before in a couple not so exciting contexts, which was about how to connect government, office, agency, whatever, to the internet using IPv6. No funny tricks involved there. It was just, that thing was never published in that form exactly, because after we finished it, some people there realized, whoops, IPv6, that's not just a network layer thing. Wah! But anyway, we got our money, and it's been combined with something else which has been published since. And about 2.5, maybe 3 years ago, I started to play around with microcontrollers. And once I got a funny thing to work, basically means you got an LED blinking. Everybody does it like that, right? So what you're going to do next? And I thought, okay, this random number generation stuff, that looks pretty straightforward. Give it a try, and if I don't get it to work within a week or so, playing around in the evening, I'm probably just going to give up. Didn't get it to work as quickly and still didn't give up. Instead, a whole lot of funny things happened. So, first off, why did I go for this? Why did I find it interesting? I have a bit of a mental framework that's slightly unusual to a lot of people. Probably not so much to you, but just to make sure you understand the thinking behind all this, I'd like to give it a bit of a rundown. So first off, when people talk about IT security, in most cases, they're lying. Because they're not talking about IT security, but they talk about IT security, well, mitigation at best. It's basically, how do we deal with the next security incident? It's not about security, but about insecurity mitigation. I don't like that. What really annoys me is that here's this brand new device, ultra high secure, blah, 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 unless you prove it's not so. And I think this is inherently wrong. Trying to find security holes in existing products to show that they are insecure is the wrong way around, really. What should really happen is that the vendors give me some plausible reason to believe that their stuff is secure, which they never do. Because there's no software without bugs, and because of that, well, here it is, and we say it's secure, and unless you prove it isn't, well, it is secure by default. Crazy attitude, really. If you want more about this, maybe explain to people who are not that familiar with the entire topic. I've done a talk at the ISTIHAG last year on the limits of cryptography, and that includes part of this discussion as well. Might be interesting for some of you just to get a reminder of what cryptography can't actually help with. But when it comes to secure hardware, we have a couple questions. First off, who do we trust if we buy these trustworthy, whatever, computing group, trusted platform module, blah, blah, blah? It's trusted or trustworthy because it's got it in the name, right? Who's involved? There's the designers, developers. There's the actual vendors. The manufacturers, which might be somebody else. Component suppliers, which is pretty much always somebody else. Logistics operators, distributors, dealers, customs authorities when things have to cross borders, investigative authorities, our spooky friends, the so-called intelligence agencies, standard issuing bodies, and who knows whoever else. There's a whole lot of people involved there, and if one of them is not trustworthy, we actually have a problem. One thing about tamper protection, because that's important when it comes to hardware. In some cases, tamper protection is actually really important. If you have crypto devices that actually hold a key store, this can be really, really difficult. If you want to take a look at this, there's a book by Ross Anderson, Security Engineering. It's available online. He's basically done a deal with the publisher that 3 years after the edition was published, he may put it online. And he has a number of nice things about tamper protection and why it doesn't work and how it could be foiled. I mean, there are things like you have this ultra high secure, this is just for my stuff, ultra secure package, and basically what you do is you take a bazooka and shoot a hole in it. Only not the big anti-tank things, but you actually get microcharges in biology, which actually manage to penetrate components, PCBs, whatever, and you get contacts in there at very high speed. He has lots of these stories in there. Very, very nice reading. But tamper protection, in some other cases, in my case, a hardware random number generator, it's not that critical because it doesn't store any key material or anything like that. And when it's unnecessary, well, it's exceedingly difficult. I just decided I'm not going to worry about that, at least not right now. And the other thing about it is, of course, it's a very convenient way to sell people stuff they can't actually check. Getting tamper protection together with auditability is really exciting. Basically means if somebody wants to fund me to the rest of my life, I'll keep working on it, I promise. But it's probably one of those things where you never really get a result that's really satisfying. Okay, auditability. If I take a TPM module from those Intel CPUs or whatever, or the crypto features in an Intel or whatever CPU, how can I audit it without destroying it? I mean, okay, so this 600 euro CPU, yeah, that was secure. That's not what I want. I want to be able to take a look at things and say, okay, yes, this looks reasonable, this looks sound. I don't find anything suspicious there, and afterwards use it. And not throw out 600 euros just for a stupid CPU. How can I do that with affordable and generally available tools? I mean, if I need some ultra sophisticated electron raster microscope, whatever, this is okay. I can afford that and a multimeter. But beyond that, and with a raster electron microscope, I wouldn't know how to use it anyway. So it's a matter of know-how as well. And yes, there are some, I've heard a couple interesting talks about people reverse engineering chips. So they cut off layer after layer on the IC and then do all sorts of funny stuff. Try to do that with an Intel CPU, or I was about to say Sun Spark, but no, it's Oracle Spark. Yeah, okay, let's forget about that. This is what I'd like to see. And the question is, how far can we actually go with that? Is auditability possible, and to what extent? And of course, the question is, what attackers are we dealing with? And that's probably where things are, well, a bit weird. The generally accepted attitude when it comes to attackers is, we are dealing with attackers, we have to assume they have unlimited resources, like the NSA, except they have unlimited technical skills, they have unlimited insider knowledge, which is basically at this point knowledge that they have, but I don't, because they have closer contacts to the microcontroller manufacturers or whatever, that have pretty much unlimited political and judicial backing. Basically, they can do whatever they want, they never wind up in jail. They happily ignore applicable laws and not even talk about decency or anything like this. I mean, they called our Chancellor Angela Merkel a terrorist. Not directly, but after all, they were only doing their stuff to fight terrorism, and they tapped her phone. Right? They get support from the manufacturers, and that's probably the biggest, most interesting thing. You assume they don't make mistakes. With adversaries like that, we're screwed. However, we might try to be a bit more realistic and take a look at real-world attackers. And even the NSA has a budget. Bigger one than I do, but we can actually see if we can make them run out of money. Because a lot of the problems we have these days with this carpet bombing, tapping attitude in the NSA and elsewhere, it's largely our fault. We've built systems where it's much too easy to do this. We've been focusing on the wrong things. And the way IT works, it's very, very easy to go for mass surveillance rather than doing targeted stuff. So the important thing is, what is the risk? What are the risks that attackers take? There's the risk of discovery. Once it's known there's some sort of Trojan horse around, and the antivirus and whatever security product manufacturers find out, it's pretty much useless. So staying undiscovered is frequently very important. And then there's a personal risk for attacker. It's one thing to tap the high frequency emissions from the monitor cable from a couple meters afar, than hacking into somebody's computer on the other end of the world. Simply because in the second case, there's pretty much no personal risk involved. Whereas if you break into, or if you come to the conference here and try to break into somebody's computer physically, if you found out, there are probably a couple of people around here who know what to do then, right? There's also the issue of an economic risk for an attacker. Again, if things get known, or if things get out of hand money-wise, that's pretty important. And what I want to do is build things that are easy to build, easy to manufacture, and that are really hard to attack using one of these untargeted blanket-style attacks. So, targeted attacks, untargeted attacks, okay, we've got that covered. Attack types. Now, you all know this, there's passive attacks, there's active attacks, right? That's run-of-the-mill standard. Okay, how about this? What is an installation of backdoors in an operational device? What about replacing an operational device? The first one might be done remotely. Might not, but might be. The second one, you have to be there physically. Much more risk involved there. So, looks very similar, completely different story. We have the targeted distribution of manipulated devices. Now that's easy. You just intercept things at UPS, DHL, or wherever, do funny stuff, and ship them on, and no personal risk for you as an attacker. Hypothetical attacker, sorry. You can manipulate entire products or product series or product lines or product families. So we have these nice new ICs doing some blah, 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 and you don't tell the customers that they also have some extra functionality. But kind of an example for that later on. We have manipulation of standards and specifications. I guess you've heard of what the NSA did working in some NIST working groups with regard to pseudorandom number generators. That's very convenient, because once it's an established standard, it's pretty much everywhere. And even then, you can go beyond that. You can go at the political level, make a backdoor legally mandatory, for example. Outlaw strong encryption, these sorts of things. And that's when things get really ugly. And that doesn't just happen in North Korea, it also happens here as well. So, what can we do? What can we do with this particular weird mindset when it comes to trustworthy hardware? There are three fundamentally different categories of defenses. First is technical. That's what I'm mostly going to talk about, and what most of us are probably most interested in. But there's also an economic thing, and that actually gets in here as well. And then there's the political issue, but I'd say Kaya's taken care of that. And Sylvia, where's Sylvia? Wow. She come back soon. Ah, okay. At the political level, that's some completely different thing I'm not going to cover here. So that's where I'm going to take a look at. And what can we do? We can make things more diverse. If there are only two commonly used operating systems on computers, like Windows and Mac OS, it's much easier for the NSA or wherever than if there were like 200 different operating systems and they'd have to hack their way into all of them. It's still possible, but it makes it quite more expensive. And diversity helps, but the way IT works, where we have tremendously high development costs but very low production costs, diversity is difficult, economically difficult. And the one thing I think we can do is make things public and make people build things from possibly building blocks we provide, but where we have serious diversity. Auditability. If people can take a look at things, and not like, okay, this is an Intel Core i7, blah, 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 but actually take a look inside what's going on. That helps. And if we make things modular, that helps with the first two because it makes it easier to build different varieties and to increase auditability. If you have a single module you can test, and then another module, and so on, much easier than one Core i7. So that was the original, or the core ideas. How do I want design to look like? First off, it has to be easy to understand. and that's difficult. It's difficult to build things in such a way they are easy to understand. When I started with this, I've built all sorts of funny circuits that I didn't even understand myself, and then just stripping things down to the point that it is easy to explain is actually quite a job. Easy to understand is one thing, easy to modify, so we get diversity. That's important. Easy to reproduce, so people can build and modify and build their own designs. Also quite important. Development tools. They must be auditable, they must be generally available, they must be affordable, if not open source, freely available, preferably, of course, and available in multiple implementations. The only way I can figure out that some implementation was messed with is if I have another one and I can compare results. So, the hardware components I use, they should be cheap. Well, because being cheap is good, right? No. They're cheap for a number of reasons. They're generally mass-produced and normally for multiple purposes. Makes it much harder to sneak anything in there. It's one thing to sneak some kind of backdoor in a 600 euro CPU. Another thing to sneak something into a 0.1 cent SMB resistor, like you've hopefully all been soldering on the badges by now. It's much easier to manipulate the big expensive stuff than the small stuff used for all sorts of purposes. Available from multiple manufacturers. Again, much easier to make all the manufacturers play along. Simple, so if you can get away without ICs, which is difficult, all the better. Things should be widely available. So even for a targeted attack, it might be difficult to figure out where I'm going to buy them, because there are like 5 different sources in the place where I'm at. Easily replaceable with similar components. Again, all to increase diversity. And easy to use for custom builds. How do I build PCBs? On your badges, no. First, something like this. That's through-hole components. And anybody can solder this as long as you know how to handle a blowtorch. That's all it takes, really. Surface mount, like you've had on the badges, is not as bad as it looks, but it at least looks much scarier. And it's okay, like you've hopefully tried by now. But, well, people might decide, no, I don't need that. Really ugly things are some of the chips on the badges that you didn't have to solder yourself, which are meant for industrial assembly only, because these you can't even check what's underneath. So, not really a good choice. I tried to stick with through-hole, at least in the first version of the board. Couldn't get everything as through-hole, but well, okay. So. That's background, theory. And then I did my little self-experiment. I decided to build a hardware random number generator. First question is, what do I use as an external interface? The one I'd normally like best is some raw analog or near analog output. Basically something that's doing TTL level kind of noise thing. And if you use a Raspberry Pi or something like that, for example, you can hook things up right away. That's cool, really cool. Except that a lot of computers don't have these GPIO, general purpose I/O pins, so I needed something else. A 5-volt serial interface, yes, you can sort of attach it somehow, but again, we're at the Raspberry Pi, and there I'd use general purpose I/O pin anyway. RS-232 is basically the same as above, except that it's using plus minus 10 to 15 volts. Everybody who's old enough should remember these. Computers once used to have them. Problem is these days you take a USB adapter, USB to RS-232, and you might have some problems in those adapters again. Another problem is that RS-232 doesn't provide power over its connector, so I'd have to have some sort of external power supply. So the immediate options are USB and PCI Express. Didn't go for PCI Express because that's real high frequency stuff, and I don't know if I want to touch that. So I went for USB, which is one crappy bit of a bus. It's a complete nightmare, but okay. So I need a microcontroller to do some processing, unless I just feed the raw near analog output straight into a Raspberry Pi. My choice there was an Atmel ATtiny 2313, the smallest microcontroller I could find with a serial interface, where there are GCC compilers available. Documentation is pretty good. They're pretty well known to the people coming from the Arduino crowd. Problem is these things, and it's through-hole. 20-pin through-hole package, so that's quite easy to solder. And to make the connection between the serial interface and USB interface on the computer, I picked an FTDI FT232RL. Yes, there's more about that in a moment. A colleague of mine, Fredrik Thulin, who's a Swedish guy working in the Cryptech project, a project initiated by Randy Bush. Some of you might actually have heard of. He's written a couple RFCs. He's been all over the place, ITF meetings, RIPE meetings, whatever. Fredrik used MSP430 for a number of reasons, and also the FTDI chip. Works. I've been to a couple of meetings with the Cryptech people, and we're just developing things, well, kind of independently, but exchanging ideas to increase diversity again, and it's more fun that way anyway. Problem here is this FTDI chip. Alternative, there's some PIC microcontrollers available in through-hole which have USB interfaces, except that the first ones here, you can't program them using open source. So I intend to test the bigger ones. I haven't got around to that yet. Otherwise, there's some bigger microcontrollers with onboard USB, which are surface mount only, which I'd like to avoid. I want to have at least the option to go surface mount as far as I can, because that'll be easier for some people. So, what's wrong with the FTDI chip? For those of you who hasn't heard about FTDI gate? Oh, quite a few people. Okay, basically what happened, FTDI has a problem that there are some allegedly Chinese companies manufacturing fake or counterfeit FTDI chips. So in September last year, they released an updated driver, which first checked is the chip on the other end a genuine one or not. And if it wasn't a genuine one, it'd brick it permanently. There are ways to recover from that if you know what you do, but most people these days don't. And they just, without warning, brick devices. Not much fun if you think about where these chips are used, because they're not used just for those PC USB to RS-232 interfaces, but for some other more important or more serious stuff as well. Basically, yeah, break things, no warning given. That means that chip must go. I'm not going to have a chip that can be remotely bricked without warning in a security-related design. Aside from the way they were protecting their business, having a chip that can be bricked like this is pretty much unacceptable to me. And I personally screwed up because when I decided to use it, I read the specs and I thought, okay, there's this one pin you have to pull low or high or whatever to program things. I mistook that. I thought you'd actually have to add a physical connection so you can program things in that FTDI chip. Okay, lesson learned the hard way. So next question is, what do I use as a noise source? There are a number of ways you can do that. One you find in a lot of books is radioactive decay. So take some Tupperware to the local nuclear power plant. Do you have some radioactive waste for me? Sure, but forget about that cup there. We'll give you a whole barrel. Just sign here. Okay. Still, you find that in textbooks. Another thing, and I know people have been using that, is radiostatic. So you set an antenna pointing straight up and use that as noise input. Yeah, you can do that. Problem is, if you are serious about security, you might not make yourself inherently manipulatable from the outside. So didn't feel too happy about that. Another thing that people have used is you take a CCD chip from a digital camera, put it in a dark box, and just read the output. And on the least significant bits of the output, you should have some noise, just by the way they work. Problem there is you've got a big chip, expensive chip, relatively expensive. So the idea is that people might actually manipulate that. Don't want that. Somebody else I found was using thermal noise in a resistor. If you run current through a resistor, you actually get noise. Very low amplitude, very low power, but you can amplify it to a point that it's actually usable. Problem there is you need so much amplification that these things are, again, easily manipulated from the outside because they're susceptible to very, very low influence from there, which then gets amplified. Somebody else, Bernd Pezon, uses, it's a ring oscillator. Basically means you take an odd number of negation gates and put them in a ring, and that thing is going to oscillate. And it's going to be one hell of a bad oscillator because it's going to be really, really frequency unstable. You could also use a microphone near a kindergarten playground. That's probably very good random noise, but I don't have one nearby anymore. I used to live near one for a couple of years. Instead, what I use is the avalanche effect in so-called Zener diodes. There are Zener diodes and there are so-called Zener diodes. Zener diodes work at low voltages. At higher voltages, you get pretty much the same net effect, but it's caused by a different physical phenomenon, which is the avalanche effect, which is pretty noisy and easy to handle, I think. Problem is you need some high voltage, and at that point, there are already two choices again. Frederick chose a charge pump, which is using an IC, couple external capacitors, and generates higher voltage. Problem there is it can only increase voltage by some factor depending on the input voltage. Good thing is it doesn't need inductances. I've used a step-up converter, standard MC3463, which is an ultra cheap. You find it in pretty much any of these small-scale USB power supplies and stuff. They're all over the place. Different vendors, ultra cheap. Everybody knows about them. They do need an inductor, but they are fairly independent of the input voltage. So even if you have a fluctuating input voltage, which is one of those things that can happen with USB quite badly. I mean, they're supposed to deliver 5 volts, but sometimes you only get 3 or less. Both work, and we have 2 different modules for that job. Cool. So much about diversity at that point. The overall layout of what I use looks like this. I've got a USB connector, a step-up converter, the actual noise generator, a little amplifier, single transistor, feed that into a microcontroller, and then through the FTDI chip out through the USB interface. That's it. Now, fun thing about noise is that nobody wants it, except me. I'm a weirdo. You take a look at pretty much any data sheet, and at best you find something there saying you'll have at most noise so and so and so, which is exactly not what I need. I need noise. I want noise. I'm a noisy person, sort of. This is was really a problem, and it's not specific to the avalanche effect. You find that all over the place. You check CCD chips for cameras, and they say noise only blah, blah, blah. You check radio transceivers, and they say, okay, noise from other frequencies no more than so-and-so. It's weird. You really run into problems with that. What happened to me? I went to a local electronics store in Frankfurt, got myself a set of Zener diodes, or avalanche diodes, sold as Zener diodes. And these are for different voltages. They're used for stabilizing voltages normally. Played around with them, and things actually worked. Perfect, right? Then I decided, okay, I'm not going to buy these sets. I want to buy individual ones. And decided, okay, I'd try a couple different types, about a dozen or so. And none of these I ordered by a specific type were as noisy as these. None. Some of them didn't work at all because the noise levels were so low I would have had to add another amplification stage. These had a type marking printed on them. Didn't say anywhere on the data sheet, but they had a type marking on there. I ordered exactly the same Zener diodes with this type, and they didn't work. The only explanation both myself and at the Cryptech project, we came up with was they're selling whatever didn't pass quality control. And that's exactly what I fucking want. But where do I order these? I mean, I'm not going to buy like a set of 300 of these, and I can only use 15 because there are 20 different voltages for. So yeah, these things happen. And there's a reason why I didn't say where I buy it, but because I took the picture from their catalog, I had put in a... Okay, so eventually in the Cryptech project we came up with, these were the magic Zener diodes. Magic because they were producing really lots of noise, way beyond what we'd expect. An alternative we found, you can also use standard bipolar junction transistors, use just the BE junction in reverse polarity. It works. If you screw up on your breadboard, well, they're only like 4 or 5 cents each. That is currently the best option we have. And it's still the question where to get noisy components. But I know beforehand that they are noisy, especially if I might actually at some point decide I'm going to do a Kickstarter campaign and build a couple of these things. Might actually happen at some time, I don't know. Yeah, that was a big surprise. Then building for auditability. How do I build a board and a design that's easy to audit? First, the circuit has to be really simple, and that takes time and effort. First designs I've used had at least 3 times as many components as the ones I'm using these days. You want to have test pins all over. You want to have a PCB layout that people can look at. Not like a 128-layer, multi-layer PCB where you have a ground layer on either outside, then some ground planes, power planes, whatever, so you can't look inside. And it should be possible to build at home if you have soldering iron and some basic stuff. This is the circuit for the actual generator and the amplifier. If you've never done any electronics, don't worry, this is easy, yes. Basically, I have something here to stabilize the input voltage, so it's impossible, or at least very difficult, to inject some high-frequency stuff there. And here's the Zener or avalanche diode. The resistors here make this capacitor go up in voltage. At some points, we get a Zener diode breakdown, where this thing breaks. Good thing is it can take that multiple times, unlike normal diodes. We get a current rushing through the transistor, which gets amplified, and we get some about 40 millivolts peak-to-peak signal out here. Use a capacitor to couple it, feed that into a single, very simple amplification stage. In here we feed 12 volts upwards. This takes 5 volts with the Atmel, or 3.3 with the MSP430, and output is near digital noise. Okay, very simple thing, very easy to explain, at least if you have a bit of a background with electronics. If you don't, well, find somebody who tells you, yeah, this is simple. There's nothing much to it. This is the board I built. In real, it looks like this. Nothing much on there. So we've got the step-up converter, which is pretty much all of this, lots of test pins around with every IC. This is where I put the diode in there. I've made that socketed so I could play around with different ones. More test pins, the amplification part, blah, blah, blah. Microcontroller with some LEDs and a programming header. This is the FTDI chip that still has to go. And by the way, the reason why I put that on a separate breakout board was when I manufactured, or when I had these boards manufactured, they screwed up, or for some reason, something went wrong with the solder mask. So I couldn't solder it onto the board directly. Other problem was with this design that I actually had to do this test pin that I thought shouldn't be used for if you don't want to program things. But thing works, and here's some noise decoupling sort of stuff. So nothing fancy. It takes me about like half an hour to solder these up. And even another problem here is this is SMD. This is an SSOP20i package. When you first realize you have to go that way, you're sitting there, I don't want to. This is SMD, and this is SSP. That means it's 0.6 something millimeter pin pitch, which means you take your average soldering iron and it spans about 3 to 4 pins at the same time. And before I ordered it, I took a look at YouTube, and here there were some people telling me, this is simple, you okay, I ordered this stuff, and these chips are about big as my small fingernail, 28 pins. Looked at YouTube again, they still claimed it was easy. Gave it a try, found out it actually is, but it's scary the first time you do it. It actually works quite simple. Just if somebody tells you you need flux for this to work, and lots of flux, it's simply not true. Flux doesn't help. The only thing that helps is way more flux, but that gets the job done. Yeah. That's the output. So basically, you can actually check if you want. I've got this stuff here. Looks pretty much the same, right? Well, at least for you too. That's the output from the first stage, from the actual generator core. And that looks noisy, sort of, especially if you look there, because that's not a movie, that's just a still. And you take individual snapshots, different time scales, different vertical scales. Yeah, and you see I haven't used proper ground, so you get some noise ripple in here. But this looks, well, exactly what you'd expect, a sine curve, sort of. Bit noisy, but okay. So this is what I get from the output of the first transistor. Second transistor looks like this, and you already see this is near 5 volt, this is near 0 volt, so this is near digital. If you change the same time scale, I don't see that too well on the screen. Yeah, you have to come down here and take a look. Basically, what you can see here on the scope proper is that the rising curve here, there are breakdowns all over the place at different voltages. So this stuff is noisy. Yeah, that's another way to look at it. That's the digital output again. Well, in case you want to take a closer look, there's a reason why I brought the scope with me. That's noise, really. So, question is, how do I turn this noise into random numbers? Easy way. Take n samples, do an XOR, use those. And yeah, that works. It's fast. it runs at constant speed, which is nice because you can then have multiple of these run in parallel. But depending on the quality of your noise source, this is going to be predictable. Especially if something breaks, it'll continue to produce output, but it's not going to be very random. And I learned the hard way. I've implemented that and then came up with a better solution, which is to measure time between rising edges. And I gathered 4 weeks worth of output, ran some tests over them and realized this is not as random as it's supposed to be. And it took me days to figure out that I've used the first approach with a Zener diode, which was not quite as magic as the one I used before. 4 weeks worth of test data. So, what I'm doing, and that works nice both in an FPGA thing like with the Cryptech people and with the microcontrollers, I just measure time between rising edges. I sample between sample values and measure the time between rising edges, which is slightly slower, which runs at variable speed depending on the input, but which adapts to the quality of the source, which is fail-safe in that if there are no more edges coming in because something is broken, it'll stop produce output. And it automatically removes correlation in inputs. Because I measure between 2 rising edges, then I do some processing, then I measure between 2 rising edges again, so there is 1 rising edge interval in between that this thing gets decorrelated. The trick to show that this can't have correlated bits in its output is basically where would I store information in this circuitry? So simplicity really helps here. It's possible to do a formal proof that it works. All that I need to do right now is test things that they are actually as random as I think, and that's a completely different problem. Question is, how do I move bias? If I have more zeros than ones, which can happen with the circuit, and I use a von Neumann extractor there, works like this. I take 2 bits, and if they're the same, I throw them away. If they're different, I take the first one. Or the second one, doesn't matter, but just have to decide when I build the stuff which one. And that means no matter how biased the input is, I will get an unbiased output as long as subsequent bits are not correlated. It took me some time to find out about that, but it's actually quite useful. Yeah. The board, I call it the ARC board, doesn't have to do with wasting 4 weeks of my life. So it's the auditable real random number generator hardware. Yeah. That's what I've got. That's what I've done so far, and there's still work to come. But what have I learned in this self-experiment? First off, ICs suck, especially from FTDI, but in general. Through-hole components suck, because this stupid thing doesn't fit on my keychain. SMD components suck even worse, and they're only topped by USB. And I'm not going to do a rant on USB here because Travis is already gone, and he'd have to hear that, or I'd do it with him together, something like that. Building auditable hardware is difficult. You put some extra work in there, but from what I've seen so far, it is actually possible. And yes, complexity is a problem, not a solution. If something doesn't work the way it is, don't try to add things, try to throw things out. And that's difficult. It's really difficult. And yes, randomness looks really simple unless you really try to build things. I guess I'll be spending a couple more years on this, so might actually come up with some more talk in the future. And what I even haven't talked about, because that's where I'm still working at, is testing. There are no real proper testing methods. There are some or even tools. There's some for pseudo-random number generators, yes, and even they are questionable most of the time, but they are not for this job. That's a different thing entirely. So I'm now back to coding C++. Unbelievable. And I also learned that testing for randomness is basically the wrong way around. What you do in statistics is that you show there is a correlation between this and that, most of the time. So all the textbook I've gathered so far, because I'm not really that fit on statistics myself, they get it wrong. Only thing that I found that is kind of useful is Knuth, Art of Computer Programming, Volume 2 from 1969. But he's still got the basics sorted out there. He's the sort of guy, he really gets into the stuff where everybody else decides, okay, this is too complex, left as an exercise to the reader or whatever. And yes, I've learned that the NIST screwed things up again, big time. Why is that? Because in FIPS 140, there are requirements for hardware random number generators in there, which take 20,000 bits in a block, run a couple tests on them, and then decide, no, this isn't random enough, throw it away, takes the next one. Which doesn't make sense statistically, because the search space just gets smaller if you do an exhaustive search attack. And they didn't explain why 20,000 bit, they didn't explain why these algorithms, why these thresholds, nothing. But some of the algorithms looked familiar. And I found them. Guess where? Knuth, Art of Computer Programming, 1969. Except that Knuth used them to test pseudo-random number generators. And not for cryptographical purposes, but for general purpose, whatever people did with computers in the late 60s. And they just copied those and said, okay, you have to test things this way. And that was scary. And no explanation given why, and that's what really upset me. There was no explanation given why these thresholds, why these algorithms, nothing. And that's basically something, that's not an open design or anything. Okay, hopefully, maybe next year or so, I have something more to tell about that. Aside from that, a couple things you might want to take a look at. There's this talk from my Limits of Cryptography. Find it on YouTube. I've got a video blog where I do some of this stuff as well. And the Cryptech project, where we're building an FPGA-based, full-blown HSM hardware security module with Keystone and everything. It's also quite interesting, quite an interesting crowd to go with. And otherwise, there's marketing again. Okay. Okay. Questions, anybody? Okay.
Hi, could you please say a few words about the underlying physical process of this noise? So where exactly it comes from?
Okay.
And actually I have a second short question.
Yeah.
Could you also say how many bits per clock cycle you can produce with your generator?
Output, this board generates, depending on the how much magic the component in there has, between 13 and 16, or 13 and 20 kilobytes per second. Frederick Tulin, who's been using a faster STM32 microcontroller, got to about 30-35 with otherwise the same circuit. The effect that's involved there is you have a bipolar junction. You've got electrons in there and positive charges, and it's in reverse bias. At some point, individual electrons will pass through because of the voltage difference, and they kick loose other charges, and that causes an avalanche effect. That's why it's called avalanche effect. And these cause a rush of current, which will quickly recover because you will run out of possible electrons or charges that can be moved. And that makes this nice to use because you don't have like a Poisson distribution for when things will next happen. You can be pretty sure it'll be in a reasonably short time frame. That's the basic thing. Beyond that, Wikipedia is probably more helpful in that than I am. Okay, anybody else?
Yeah, wait.
Okay.
Great talk. Out of curiosity, how do you provide people that use your implementation with testing if the diode that's used, which is obviously a potential weakness, is actually a good one for the purposes of random number generation?
Okay, the diode is not that much of a weakness because, well, it's a two-pin weakness with regard to manipulation. It's a two-pin device, very little voltage going through there, so you can't fit a microcontroller or whatever in there. If it breaks, and you use this edge-to-edge detection, wherever you process the noise that doesn't come up anymore, the output will stop. If something breaks, this design will stop producing any output at all.
Have you considered implementing the USB stuff in the microcontroller itself, leaving the FTDI completely away?
Yes, there are a couple of ways to do that. First one that doesn't work is called VUSB, which is a USB. Let me find the list. VUSB, which is a USB 1.1 implementation, and that's too slow.
Okay.
It's simply too slow because the microcontroller here is really busy. It's the key thing that slows things down. Other thing is, why I want to take a look at these PIC microcontrollers is they have USB built in. So that might actually be an option to get it out fast enough without having to go SMD again. And otherwise, the bigger microcontrollers, a lot of them have USB on board as well, but that's stuff you don't want to solder yourself necessarily. So there is no one-size-fits-all solution to that, but I want to cater for different people and increase diversity. That's the idea, really.
Okay, thank you.
Okay, so Benedikt, thank you very much.
You're welcome.